secant, tangent, trigonometric integrals. Very similar to the idea with sine and cosine trigonometric integrals. When we have integer powers, the goal there was to isolate or pick out one term so that we either have sine squared or we have cosine squared, because if we can get to that, then we could use the Pythagorean identity and get the answer. Last time we did a bunch of cases with secant and tangent, and we realized some work, some don't, right? What is the first case that we did that did not work? We will save it for the last today. Okay. First one had a cube power of secant. We'll get to that later. The second one was secant raised 4 and tangent squared. Secant, right? You're making a face.
Yeah.
Wait, yes to making a face or yes to?
No, I wrote something down.
Okay, so it's the correct one, right? Secant raised 4 tangent squared. Okay. I guess it's good to know now later when we do sequences, it'll probably come out. If I have 2k, I'll be a lot richer. But k equals 0, 1, 2, 3, dot, dot, dot. Every single number, when you plug it in for k, you are going to get an even term, right? An even number. If I had 2k plus 1, right, then when I plug in, I will get an odd integer, right? For the start, when we get to sequences and series, you will learn about it. That is the general term for an even numbered sequence, general term for an odd numbered sequence. Something you've got to know. So we can write in general terms, or k equals 0, 1, 2, etc. Technically, k equals 0.2, etc. So that would guarantee us that the secant is always a odd powered term, tangent even powered term. When it came to sine squared and cosine, trigonometric integral powers of sines and cosines, our goal is to get to sine squared plus cosine squared equals 1 identity. Here, our goal is to get to secant squared equals 1 plus tangent squared identity. And I showed a whole bunch of cases last time. I said whatever that works for secant and tangent will work for cosecant, cotangent. And if you looked at the relationships closely, secant tangent relationships will turn to cosecant, cotangent with a negative popping up here and there. So if you remember these, you can get to those easily. So whatever works here will also work for cosecant, cotangent integrals. Good. Okay. We want to get to secant squared x. So secant raised 2k. Yes. At this step, what should you do? First, this is the case that we want. I think I'm might go on, what is it? What was that second problem?
Or tangent squared.
Make it even. That is the first case. So secant raised 2k and tangent equals 2k. Let's do this first. So even power, and if we pick u to be tangent x, what is du?
Secant squared.
Secant squared x. There are only one of two possible substitutions from last time. Either you pick u to be tangent x, or you pick u to be secant x. And you would end up getting du to be secant squared x dx, or secant x tan x, or tangent x dx. So in this case, if I pull one secant squared out, again, combine those two, 2k minus 2 plus 2 would take you back to 2k, right? All I'm doing is separating the powers as 2k minus 2 and 2 there. Going to rewrite this as tangent x raised 2k dx. Good. What is our substitution here? Of the two, which one should you pick? U equals tangent x or u equals secant x? We did this last time as an example. Second case that worked, or the first case that worked. Secant raised 4x tangent squared x. What was our substitution? Tangent. So if I pick u to be tangent x, the integral would simply become u raised 2k. Secant raised 2k minus 2x, I can rewrite it as secant squared x raised k minus 1. Power of exponents, you multiply 2 with k minus 1, you would get 2k minus 2. Good? The remaining part, secant squared x dx, would simply be du. And we're almost done. What is the last step? Right in terms of tangent. 1 minus tangent squared x raised k minus 1. U raised 2k times du. One more step and we are done. So integral 1 minus u squared raised k minus 1 u raised 2k du, depending on the value. Yes.
Well, wouldn't that be 1 plus u squared because the identity?
Yes, you are correct. 1 plus. Depending on the power, k minus 1 to k, you may either have to use integration by parts or FOIL and integrate. Last time we simply FOILed and integrated and we got the answer. Agreed? So the case here even power of secant, even power of tangent would mean the substitution would be tangent x. That would be your substituted integral. You should put this on your cheat sheet. Now, will I recommend you do that? No, technically no, because you've got to know how to get to the answer for future courses. But to reduce the level of stress, put it in your cheat sheet. Even power of secant, even power of tangent, substitution is tangent, integral would be that. Good? From that point onward, it's up to you. Either you FOIL and integrate or integration by parts. Clear? Good? Yes.
I'm a little confused on how you did k-1 after you like did the
From here to there.
Yeah.
So I wanted secant squared x.
Yeah.
Right? Otherwise, I can't do the substitution. What is a squared raised k minus 1? You don't know?
I don't like when we do like general stuff. Like it confuses me.
Very true. I didn't want to, I started with individual cases, and I'm going for the general case with secants and tangents because they're not as straightforward as sines and cosines. So if you have some number raised to the power or something, raised to the power of exponents, you multiply those two. So a raised 2 times k minus 1, which is a raised to k minus 2, right? Instead of a, I have secant. Good?
Yeah.
So I wanted to get to secant squared. So a squared raised k minus 1 would simply be a, which is secant x, raised k to k minus 2.
So that's saying the same exact thing.
Yes,
Okay.
I'm just rewriting it so that I can substitute you. Megan, you have that page?
I don't even know. Like, where did the 2k minus, like, I know you just explained it, but why did, I didn't know you did it because you want the secant squared x, because otherwise you can't do u sub. But the secant 2x minus 2 just, it does not really make sense to me.
Okay. So do you know how I went from here to there or no?
For part of it, yeah, but not for this, the right side, yes. Like
This,
the tan and the secant squared, that makes sense.
okay, so this makes sense also.
No,
No?
no.
Because it went from here to there.
Okay, how about I write that secant raised to kx? Again, I wanted to do it in a very generalized way because secant tangent integrals are not as straightforward as sine, cosine. Sine, cosine, integrals, you can look at it, carefully and with a bit of trial and error, you can get to it. But secant tangent, probably go in circles, and I don't want you to do that, which is why I'm writing a generalized version. So, just to clarify, secant raised to kx. I can write it this way, do you agree? Okay. Which I can also write. Now, do you agree? Which, I split the powers, bases are identical, right? Secant raised to k times secant x raised to, yes, times secant x raised negative 2.
Yeah.
Just split them up.
Mhm.
That term, secant x squared, is nothing but
Oh, then that,
that term.
okay. Oh, so then you just combine.
I
the other
combine
two.
those two to get 2k minus 2.
Okay. That makes sense.
Good.
Yeah.
And the other part, once I have them combined, secant x raised 2k minus 2, all I'm doing is rewriting this as 2 times k minus 1, right? And move that 2 inside, going back to that step. Good?
Yeah.
So, if you have an even power of secant, even power of tangent, the substitution is tangent x, you would end up with that integral. Good? Standard procedure. From that point onward, is it going to be foiling and integration or integration by parts? It's going to vary based on the value of k. Now, what is the second type that worked last time? Another is type 2. So depending on the value of k, I can plug in k equals 0, 1, 2, 3, 4. Or 1, 2, 3, 4. Both powers are odd. Secant has an odd power, tangent has an odd power. What did we do?
Split both.
We split both of them. If you split both of them, I can rewrite it as secant raised to kx times secant x. Tangent raised to kx times tangent x. Yes? And there are only 2 possibilities for substitution. Either u is tangent x or u is secant x. In this case, what is u? Secant x. So let me rewrite that this way. I'll explain in a second. Secant, tangent, I wrote it there. The ones that I pulled out. Pulling the k out, so I'd have a tangent squared term. Here, I'm pulling 2k out because substitution is u equals secant x. Agreed? So if u is secant x, in this case, u raised to k. What is the derivative of secant x? Secant x, tangent x, so I could get that part. Great. What should I do to the middle part? Okay.
1, no. Yeah, 1 minus secant squared, no.
1 minus secant
No,
squared or is secant squared minus secant squared x minus 1 is tangent squared going back to that, so u squared minus 1. And raise the power of k. From here, whether you FOIL and get to the answer, or you do integration by parts, it is going to depend on the value of k. Good? If that power exceeds, 4, I will not recommend using, 4 is a bit large to begin with, correct? So, if you have an odd power of secant, odd power of tangent, then the substitution will always be secant x. The integral would change to that, which would be easier to integrate. Agreed? Type 2. What was the third case? Yes,
I'm kind of confused about the third line and then the.
oh, speak up, I can't hear you.
I'm kind of confused about the third line
Uh-huh,
and then how you got the u squared minus 1 out of that. Oh, wait, no, I see this.
I didn't see. And what was the next one? The third case that worked, the fourth type that we did. So we started with even power, odd power, odd power. We did another case, odd tangent, even secant, right? So even secant, odd tangent, that would be type 3. What should I split up naturally? The one that we've got to split up would be the tangent power, right? If I pick u to be tangent x, and du would be secant squared x. So I need a secant squared term, so do the same trick that we did with type 1, 2k plus 2 minus 2. So this part will become a secant raised to k minus 2. Secant squared x. Split that, tangent raised to k x, tangent x dx.
Why do you split the secant like that?
Because I'm going to use a substitution. U equals tangent x. We don't have to split this one. So, if I pick u to be tangent x, because those are my only two options. Either I do tangent x or I do secant x. If u is tangent x, du is secant squared x dx. So the tangent x part, I can rewrite it as u raised to k plus 1. Secant squared x dx will be du. Good. That leaves us with one term. Secant raised to k minus 2. What do we do about that? What did we do in type 1?
Secant squared.
Make it secant squared. So secant squared x raised k minus 1. Same thing we did over there. We need tangent. What do we know about the relationship between secant and tangent? Secant squared x is equal to 1 plus tangent squared x. So that would be 1 plus tangent squared x raised k minus 1. Good. That's it. So if I have an even power of secant, odd power of tangent, then my substitution would always be tangent x. And the integral would change to u squared plus 1 raised k minus 1 times u raised to k plus 1 du. From this point onward, whether you use integration by parts, FOIL, entirely up to you. Good?
So if you got a problem and you knew the exponents, how would you use them?
I'm getting there.
Oh,
I'm getting there. The case that failed. The very first one. Last one. And What's power for secant? An odd power for secant, and even power for tangent. That is the case, that's going to be painful. Good. So secant, tangent, integrals, 3 types, straightforward. Odd power of tangent, even power of secant. Both powers are odd, both powers are even, piece of cake. Odd power of tangent, painful. Good. Is it doable though? Absolutely. Good. Okay. I'll show you how. Erase. So those are the 3 types.